Words of welcome from me. I'm David Wallace, Director at the Institute. Delighted to see such a good audience for this workshop. I'm sure it's going to be really interesting, both in terms of the content that you've got and the people that are here. I think that's fantastic. For those of you who haven't been at the Institute before, just to say that if there is any way that the staff can help you, any queries that you have, please don't hesitate to ask. And the staff here are simply dedicated to making sure that you get the most out of this workshop and are free to work and to interact with people without any organisational distraction. So they're here to help. Please don't hesitate to ask them. They'll help in every way that they possibly can. And another thing that I should say is just by way of thanks to Ian and Mike and the other workshop organisers. Extremely grateful to you for the work that you've put in pulling this together. And I'm sure it's going to be a great week. And I think the last thing that you want me to do is actually to go on at length, so I'm going to stop. That will be the last thing. Thank you all very much for coming. I hope you have a great week. And I think it's over to you, Ian. Thank you.
Thank you, David.
Yeah.
So thank you, David. And I too want to be brief, but this is not only a workshop, it is also the concluding week of this program on high-dimensional data analysis. And I would actually like to take just a moment to, on behalf of the organisers, to thank and all of us to thank particularly Mike Tiverington, because our other organisers, Peter Bickle, David Banks, and myself, and the Scientific Advisory Committee, of whom Peter is a member, we are in a particularly privileged position to see how much work the lead organiser for a program does, from the assembling of the proposal, to the corralling of the scientific leadership, to the meeting of deadlines, to the conception and initiation of the workshops. And then during the program, I'm sure many people know from their own experience in a department how important a role can be played by a person who is sort of the scientific and social cohesive force for an enterprise. And through being here the whole time, Mike has played that role in so many ways, even unto things like my favorite email message explained that May week was a term that was 100% accurate, except for the fact that it happened in June and that it lasted longer than a week. So over the entire spectrum of activity, we have so much to thank Mike for over this program, so let's give him a hand. So we turn now to the opening talk of this meeting, and it is an enormous pleasure to introduce he who needs no introduction, Peter Hall from the Australian National University. That is so ingrained. He is now from the University of Melbourne, and he has come all the way to speak to us on very high-dimensional regression and classification.
Thanks very much, Ian. Thanks for that warm introduction. Yes, I have a personal appointment at the University of California at Davis too, and it was there. Oh yes, I must turn this on. Thank you very much. It was there that I had a slight incident with a bike a couple of weeks ago, which is why I'm hobbling around a little. So there's no need to feel any sympathy because it's much better than it was 2 weeks earlier. The title actually goes back a lot further. I had to be fairly general because I hadn't decided what I would talk about. It looks very grand and pompous, and it's not intended to be that way. I'm just trying to talk about a few things in that sort of connection. Thank you very much for inviting me, Mike, to join the committee, wherever you are. Oh, there he is. As Ian said, it's been a wonderful time, a very long period. As you possibly don't realize, though, those of you who are here, you don't. I didn't realize until I took part in this enterprise. It must be like launching a space shuttle or something. Except I suspect that launching of a space shuttle doesn't have the same complications that Ian noted about unusual uses of the English language. And so it's really been an honor to be part of the organization of the meeting, and I'm very jealous of those of you who are able to spend a longer period here than I. The work I want to talk about is joint with Hugh Miller, who's a PhD student at the University of Melbourne, and I want to talk a little about some particular viewpoints and particular methods that we have for variable selection and classification of high-dimensional data. And I'm going to begin by making a few comments on the what's probably the most widely used approach, which is to assume that we have a response variable yi, which is a linear function of the components of the explanatory variables, of the vector of explanatory variables. Yi is sometimes a genuine response in that it could be a quantity observed in the continuum, and the xi's are almost always fairly typically explanatory variables in the sense that they represent a vector of the expression levels of a largish number of genes between a few thousand and a few tens of thousands. However, in a large class of problems, yi is either is generally an indicator function, could be a variable that takes just the values 0 or 1. Occasionally it takes more values than that. When it takes the values 0 and 1, we are generally endeavoring to classify a person with a new vector of expression levels as coming from one population or another, where the two populations might represent different sorts of cancer, or one sort of cancer versus no cancer, or something along those lines. Although the fitting of the linear model is generally viewed in that as a relatively conventional problem, the explanatory variable on the left-hand side is often not observed in the continuum, in fact. And there's a very wide variety of methods which over time seem to perform increasingly well. Not only do the new methods generally perform better than the older methods, I guess if they hadn't, then they wouldn't have been newer methods. But secondly, over time, we're developing new ways of making older methods, like the lasso, work that much better. So these are all competing techniques, and they are all very widely used in practice, except for the most recent ones, which have only just appeared. Okay, so I mentioned here something about the typical applications where Xij represents the level of the represents the expression level of the jth gene of person I, and yi might be just an indicator function. In cases such as this, I think we would agree that the linear model is probably not something which is particularly accurate. And even in cases where the yi's represent a genuinely continuous response, the linear model is something of a surrogate for issues that are much more complex, that are linking the response variables to the response variable to the explanatory variables. Nevertheless, even though if we use the linear model for prediction rather than variable selection, we would almost certainly get an inconsistent result. That's not necessarily a major problem for us, as long as the response is in some sense qualitatively linear in the explanatory variables. By qualitatively linear, I mean something which is monotone and doesn't change too fast over the range where it's monotone. So linearity can be a good approximation for many practical purposes where things are not exactly linear. However, perhaps I should note first what's in initial paragraph here, a remarkable paper by Peter Bickel, Yahav Ritov, and Sasha Tsibakov was, I think, completed only last year, showed that many of these methods will have inherently similar performance. So this is the nature of the problem, not necessarily the nature of the methodology. So many of these techniques, such as the lasso and the Danzig selector, different approaches to variable selection through the linear model, will give results that are not strikingly different from one another. One can reasonably ask, are there penalties, are there impediments or prices that we have to pay for taking a linear model approach to solving these problems, not least because many of the different approaches will give similar results. And one of the points I want to make here this morning is that I think there are downsides to this. I think we can miss information in important ways, and I think there are simple ways of accessing information that is missed through a linear model approach. In particular, there's a risk that that fitting an incorrect linear model will lead us to overlook a number of influential components in the vector of explanatory variables. For example, if a particular component is highly correlated with another, if the first of those components is one on which or for which the linear model is a really good approximation, and if the second one is one where the first component is which the first component is a fairly nonlinear function, then the second component won't be detected typically won't be detected using a procedure which is based on fitting the linear model. And I'm going to shortly show you a practical example that motivated us along the path of the methodology that I'm going to describe of exactly this type, where you have two components where one appears to be a highly or significantly nonlinear function of the other, yet the two are highly correlated, and therefore you would expect that both of these components, not just one of them, would be of biological interest, yet the second component typically isn't picked up using a linear model approach to variable selection. And more generally, using an ill-fitted model to solve a variable selection problem, particularly when that model is aimed at prediction rather than variable selection, will obviously have its potential risks too, and I'll look at a practical example that's related to that problem. Okay, so perhaps just to quantify very briefly from a theoretical viewpoint some of the issues that I've just discussed here, let's suppose that I can write yi equals xi1 plus error, so the linear model fits perfectly through the first component, and let's take xi2 to be highly correlated with xi1, but doesn't actually appear in the model, perhaps because xi2 is a nonlinear function of xi1 or a nonlinear function of xi1 plus noise. One of the advantages, I should say, of the methods that I'm going to talk about is that they're relatively not susceptible to problems caused by errors in variables. Potentially competing approaches are more susceptible. I'll have a little bit more to say about that shortly. So this is that's a very, very babyish, very elementary theoretical quantification of the problem I mentioned earlier. There are also some related issues which you can also see evidence of in practical examples, where a linear model is close to not being identifiable. So, for example, if one gene, or perhaps I should say, if the expression level of one gene is a linear response or approximately a linear response in the expression levels of other genes, perhaps subject to errors in variables, then you may face identifiability issues in terms of fitting the linear model and in determining influential variables from that viewpoint. Okay, now in order to illustrate some of the points that I've been making here, I want to look particularly at two practical examples. The first of these the first of these examples uses data that were employed, I think, first by Siegel in the variable selection problem to evaluate various approaches to let us say dimension reduction in regression based microarray analyses. And the aim here was to determine which genes were influential for overexpression of a particular protein coupled receptor in mice. And the research was aimed at understanding certain types of human heart disease. This is an example where the response variable is actually measured in the continuum. Of course, in the continuum modulo the rounding of the data. It's not an instance where the response is just an indicator function of one or two or a small number of different populations. So here there were the sample size is moderately large, n equals 30, and the number of dimensions is moderately typical of this sort of problem. P is 6,319. Now, the approach that I'm going to illustrate here is based on ranking the generalized correlation of the responses for particular components of the vector of expression levels. That is the correlation between the jth component of the vector xi and the response variable yi. And the generalized correlation that I'm going to look at is going to be based on, you can think of it as cubic polynomials. That gives something almost the same. We actually fitted cubic splines. I'm going to look at the supremum of the correlation, or the empirical correlation, computed over all possible functions h of xij, where h is chosen from a class of cubic splines. The reason for choosing cubic splines, perhaps I should say, I could simply take h to be the class of linear functions, and then I would get for my correlation simply the absolute value of standard correlation. But that would be looking at linear relationships and wouldn't appreciably overcome some of the challenges that I've suggested that methods based on fitting linear models might be up against. By looking at quadratics, we run into problems because a quadratic is not basically either an increasing or a decreasing function. It goes up and it comes down again. And many real world responses are not of that type. Many real world responses are basically monotone, except for something which strays from monotonicity in the middle. They're kind of like a monotone response with a blip somewhere. And these are the sorts of things which cause problems. And that's the motivation for looking at the correlation, or rather the maximum of the correlation over functions h of xij and yi, rather than where h is a cubic spline or a cubic polynomial or something like that, so as to capture that kind of potential blip. And yeah, so that's what I'm going to use in this analysis here. And this was applied to these data of Siegel and his co-authors. And it led us to rank two genes, first and second respectively. The first of these was no surprise, since it was identified very quickly. I think it might have been the first ranked gene in a linear model approach, but the second wasn't touched. wasn't put forward in any obvious way by the linear model approach. And we can get an idea for why this might be the case by looking at a graph of the response of the a graph of the response variable against the explanatory variable on the horizontal axis. This is for the first gene, and you can see that the response in this case is not far from monotone. It's plausibly monotone, in fact, just about all the way through, and it's plausibly linear. And that's the sort of response that I would perhaps refer to as qualitatively linear. Fitting a linear model is not going to cause us any grief. In the second instance, however, you can see that we have a blip here. We have a response which is basically linear, basically linear, although of course it goes the other way. It's a decreasing function rather than an increasing function of the expression level. But for one reason or another, perhaps because these responses up here can be viewed as outliers, or whether they're true or not, this is not really an issue on which we have to pass judgment. For the methodology that I'm talking about, there is a blip in the model, and that nonlinearity or non-monotonicity is the reason why approaches based on linear models don't identify this second gene. I should say that the correlation between if I'm what have I done? I've gone the wrong direction. There's a strong correlation of minus 0.75 between the expression levels for these two genes, and of course the negative sign reflects the fact that one is an increasing function, the other one's a decreasing function, and the 0.75 indicates the strength of the relationship. But this is, I believe, an instance of the masking effect that I mentioned earlier, where you can have two variables which are highly correlated, but because one is not a linear function, or the expression levels for one are not linear related in a reasonably close way to the other, not monotonely related in this case. This is an example where you'll pick up only one of them and you may miss the other entirely in taking an approach based on a linear model. Okay. The second example I want to look at is one that's become something of a benchmark data set for the analysis or for the comparison of variable selectors, and it uses data from a study by Golub and co-authors in the late 1990s, where the aim was to use microarray evidence to distinguish between two types of acute leukemia. There are 7,000 odd genes, gene expression levels in each vector of explanatory variables, and their sample size is 38. So the parameters in this sense are very similar to those given previously. Now, here we used a technique which is again based on correlation, but here we were very babyish, very elementary. We used simply linear correlation, and we simply took the view that and I should mention here, this is crucial to our approach to analysis, that the y's take only the value 0 or 1. You're looking essentially at a classification problem, assigning to one population or the other. Here, the fact that the y's are binary indicates that they could be treated by minimizing a deviance formula for Bernoulli data with a logistic link. And so we looked at trying to minimize this quantity here, where we could have been fancy and taken H to be a class of relatively interesting functions, but we took it just on this occasion to be the class of linear functions. So again, it's a correlation-based approach, but this time it's really based on very conventional linear correlation. So we took H to be the set of all linear functions. Now, in broad terms, there's no surprises here, as you might expect. This is a benchmark data set. It's been very strenuously analyzed by many people, and there are some absolutely outstanding and remarkable results out there. And we have a very elementary method here, which we're really just trying out on this approach. So, and of course, as I said, we're just trying out on these data. Of course, as I said, this is a classification problem. So we constructed a very simple classifier. We took the genes that gave the 5 largest values of that quantity that was in the transparency just over the page here, this formula 1 here. We chose 5 because 5 is odd. I'm going to use a simple majority vote method, and if I take 5 genes, I'm not going to have any ties. 3 didn't do quite as well as 5. 4 gave us some ambiguities. So we, let me see, one of the nice things about working with mathematicians is that they believe in blackboards, and that's a big help. I think whiteboards are a retrograde step in the evolution of university lecturers. So we have the 5 genes, and for each gene we identified by a repeated application to the training data a level for which above that, we identified the level by trialing with the training data repeatedly, a level which gave us a good classification rate if we assigned 1, 2, 3, 4, 5, if we assigned or if we asserted that the population was one or the other, depending on whether the value of the expression level of that gene exceeded a given level or not. And we did that for each gene. And then we applied this very elementary, very babyish classifier to the data for these levels chosen from the data. And we assigned an individual to a population depending on which population the majority of the genes taken individually would have assigned that person to. And we got results which are similar to those obtained by others, except that bear in mind we're working only with 5 genes here rather than with the much larger numbers or somewhat larger numbers chosen by others. So we were able to get just 1 test error from trialing just these 5 genes. And the 5 genes that we label using our approach are different from the ones that have the top 5 ranking. For example, in the different approach that Mike and Jing Hao and I have done in related work. So there are, although in that problem we can get good classification with fewer than 5, although not quite as small training errors and test errors as we get here. I should try to indicate why I think things are working reasonably well for us here. The reason is that we are not focusing on the problem of prediction, on predicting a good value of y. We are focusing instead on the problem of trying to identify a smallish number of influential variables using an approach which in this problem is linear in some sense, in the sense that we took the class of functions h to be linear functions, but in general can be a nonlinear method. You can change the class of functions h to suit your problem. We find that cubics generally give us quite good results. But so I think that any advantages, and you may not agree that there are advantages, but I think that any advantages that the method does have are a combination of these two issues. First of all, we're not treating the variable selection problem as one that's inherently of prediction. And secondly, we are allowing, I guess you could describe it as a user-choosable level of nonlinearity. How am I going for time? Plenty, okay. Okay, so having perhaps gone about as far as almost as far as I want to go with these numerical motivations, I should be specific about exactly how we construct our method, and it's really very elementary. As I said, it's based on correlation, and it's based on generalized correlation. So I look at the covariance of general functions of a component x of the jth component of a random of my vector of expression levels with the response variable y, and let me see if I get this right. I've forgotten what button to press. Maybe it's this one here. No, doesn't matter. That display on the left-hand side is basically just ordinary correlation with the supremum taken over my class of functions. On the right-hand side, of course, I have its empirical form. So the quantity on the right-hand side is just my estimator of the quantity on the left-hand side. You'll notice, of course, there's a bit of junk in the... Hi there. Not a problem. I need to do a control L, I think. Not a problem. I wasn't even capable of doing that, so that'll do it. No worries, Neon. Thanks very much for trying. Except that I need to go back a bit. At least I'm able to do it. Sometimes I get stuck and I won't go anywhere when this happens. There's a bit of junk in the denominator, the variance of y1 and this sort of empirical thing up here, which doesn't depend on the component index j, so I can toss that away. So we actually finish up ranking the values of these guys. Ah, wonderful, tremendous! I can even use this to support myself. Thanks very much. It gives you a certain air of authority, doesn't it? To be able to wield a stick in front of an audience. So this is the quantity we actually use. Now, I'll say something right at the very end about theoretical properties of this, and they're not particularly difficult to work out. They're all based on moderate deviation probability formulas. And one thing which we haven't exploited in that theory, which I think is potentially exploitable, is the fact that what we have here is, of course, is something like a studentized ratio. We have a numerator of which the fluctuations, at least insofar as they're due to largish values of the function of the explanatory variable, or the jth component of the explanatory variable, are also reflected in the denominator. And this is an inherently stable beast, and it's becoming known in recent work in probability theory, I guess recent over the last decade, that studentized ratios and their analogues have some really very nice properties, in the sense that their behavior can be worked out under very mild conditions, under very mild moment conditions, for example, on these quantities h of xij. And although we haven't gone down this path and we haven't tried to economize on the moment assumptions that we need to get our theory to work, I believe that this kind of result can be obtained. So what I'm trying to convince you of is that there is some virtue in this type of ratio where the numerator and the denominator have that studentized form, which means that there's a potential for large fluctuations in the numerator to be dampened down by large fluctuations in the denominator, and so for this quantity to be more robust than it would otherwise be. People who are responsible for these theoretical results include Xiying Wang, who I think is currently at the University of Sydney, but particularly Ximan Xiao, who's at the University of Science and Technology in Hong Kong, who has some remarkable results in this area. So I guess I'm doing just a little bit to say that's not such a bad thing to be working with anyway. Okay. If we were to restrict the set H that or the set script H to linear elements or to linear functions, then we would obtain just the absolute value of conventional correlation coefficients. So if you do that, you get something that that actually has some advantages. So there are some uses for that. I should say something about it perhaps if I have time at the end. But the really interesting part is where you allow H to be nonlinear, or to be a class of functions which include nonlinear functions, and that enables you to capture nonlinear relationships and indirectly to identify vector components that are nonlinear relationships of one another, which might be overlooked by a fitting approach that was based largely on the linear model. I should say too that the optimization of these, the optimization, here the supremum has a simply computable explicit solution, which is just the least squares solution in the obvious problem from which this derives. So computation is very straightforward. There's absolutely no problem in cycling through a vector of length thousands or tens of thousands to do all these calculations. So that's a good outcome, although I must admit it wasn't something that concerned me initially. Now, of course, having got these correlation coefficients, and these are the guys I called psi j hat a little earlier, I then rank them from the largest to the smallest. These guys are all going to be non-negative because they're suprema, and simply by changing the sign of the function h, I can switch something from being positive to negative. So I simply rank these guys, and this gives me some sort of empirical ranking of the components of the explanatory variable x. And here I should perhaps have put this phrase here in quotation marks in order of their impact expressed through a generalized coefficient of correlation. I am here effectively defining what I mean by impact expressed through a generalized coefficient of correlation. So this notation that j is ordered larger than j dash means formally, or is defined by, psi j hat being greater than or equal to psi j dash hat, and informally it means that our empirical assessment based on correlation suggests that the jth correlation of x has at least as much influence on the variable of y as does the j dashed correlation. Okay, now that's all very well. That gives us some sort of point estimate of a ranking, but what I need to do is get a little more information. I need some account of the authority of the ranking. And this proves particularly useful in practice. So for example, shortly I'll go back and I'll look at the first of the two practical motivating examples, and we'll see there that it's actually quite important to have these bootstrap methods that I'm going to describe in a moment, because they show that these two guys that we pulled out, you recall in the from the data of Siegel and co-authors, the first gene that we identified is something that everybody's aware of. The second gene is something that has in the past been pushed into the background. This using the bootstrap to assess the authority of what we have done here makes it fairly clear that the second gene really is something that we should look at seriously. It's not just a chance occurrence. Okay, so we simply apply the same procedure that I mentioned a moment ago to a resample drawn by sampling randomly with replacement from the original data set, and I compute confidence regions at a nominal level, such as 0.05 such as 1 minus 0.05 or 1 minus 0.1 or something like that. I compute two-sided, equal-tailed, standard common or garden percentile method prediction intervals, not confidence intervals, for the ranking. These confidence intervals will have a lower endpoint and an upper endpoint, r hat minus and r hat plus, respectively, and I can then I can plot those confidence intervals. If those confidence intervals are short, then I can assume that I have a fair bit of confidence about the particular ranking that I obtained. If the confidence intervals are longer, then I have less confidence about the prediction intervals are longer, I should say. Then I have less authority associated with my ranking. And I also plot on the confidence prediction interval, the value of r hat of j. We have empirical methods for choosing alpha, so that's not an issue, although it does turn out that in practice choice of alpha doesn't have much bearing on the conclusions you draw. The conclusions remain much the same for a variety of different choices of alpha, but we have techniques for choosing alpha empirically. Okay, so let's go back and look at the first example of these two genes that we identified from 6,000 odd. The first gene is something that is known to be, or has been identified often before. The second, less often. It certainly hasn't been up there among the top few genes identified earlier. And I remind you that in this particular example, we used a generalized correlation approach based on cubic splines in order to identify genes that were of particular interest. And I'm going to put up next the bootstrap method that we used to construct, in order to shed some light on the authority of the ranking. The way in which we present these data depend very much on how many genes you have. Sometimes we present each of these lines here represents a confidence interval, prediction interval, with one end of the interval being one end of the prediction region and the other end being the other end of the prediction region, and the horizontal bar marking the rank that was given to us for the initial data set, of course, as distinct from a bootstrap resample drawn from that data set. Sometimes we plot these things vertically because it manages to get everything into a nice, relatively small space. Sometimes we plot them horizontally. Don't think anybody's going to be too upset about that. These two genes are the first and the second ones that I mentioned before, and you can see that there is a significant jump from the second to the third. So we feel that this poor overlooked second gene actually does have a significant relationship to the response variable yi, even though that hasn't generally been reported in the past. And of course, once you've gone beyond the first and the second of these two genes, then you're into the also-rans, which also have relatively short intervals, but nowhere near as short as in the first two instances. Okay. Now let's go back and look at example 2, and I don't really have very much extra to say here, except to show you the version of the plot, in this case, in this instance, the version of the plot that I put up earlier for example 1. Okay, here we stacked the confidence prediction intervals one under the other, with the top ranked genes being the first. So again, each interval corresponds to the prediction interval for the rank of the gene, and it gives us some idea of how much surety we can, or how much assurance we can place on our alleged ranking. And again, the little bar here represents the actual rank computed from the data set. And you can see that the first two ranked genes have a lot of impact, or appear to have a lot of influence on the value of the response variable. And there's, once you go from those first two, the next three we have less assurance about those, and the degree of assurance is pretty similar for the next, I think up to about 9. My memory is that this guy is about 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that's 9. That's the 9th gene. And then there's another jump down where we lose a bit more confidence in the authority of our ranking and so on. Okay, so I mentioned that we looked at the first 5 of these in order to construct our classifier, and we needed an odd number of genes because we were using a method that was based on a majority vote among the genes. Okay, that's almost all I have to say. So you're going to get an early mark for being such a nice and quiet audience, except to say that one can do a bit of theory for this, and the theory is all of the sort which says that if the actual generalized correlations are more than a certain amount, then with probability tending to 1 as the sample size and the number of components of the vector of genes increase, you will rank all of those special components ahead of all of the other components. Let me see if I can quantify this a little bit by pulling out the most important features here. Okay, I'm assuming my sample is of size n and that my dimension is of size p, and I'm going to allow p to increase no faster than polynomially in sample size, but it can increase at any polynomial rate. So it's to be no larger than some constant times c to the gamma, where c and gamma are positive numbers. And I'm going to assume that for each n, I have a number, say q, of correlations, all of which are larger than some constant multiple of the square root of n to the minus 1 log n. I can think of this as a triangular array problem, where for some q among the p at the nth level of the nth row of the triangular array, all of the generalized correlations are greater than some constant times root n to the minus 1 log n, and that all of the other correlations, that is for the p minus q random for the other p minus q components, are of little o and root n to the minus 1 log n uniformly in their component indices. I think I'm thinking here of taking q to be fixed and p to diverge, so I'm only thinking of identifying a relatively small number of genes out of a large number, which is the background indicated by the real examples that I've looked at, but there wouldn't be any problem in allowing q to increase not too fast with n and p if you preferred that approach. Now, the regularity conditions on the x's and y's are that they have uniformly in their index and uniformly in all levels of the triangular array, they have at least some polynomial number of moments, so the expected value of mod x to some constant is finite, the expected value of mod y to some constant is finite, where those constants, the values of those constants are determined by gamma. I guess C might come into it, but it hardly enters into it at all. And the constant multiple of n to the minus 1 log n to the half also comes into the size of the constant, or into the number of moments you need to assume. So if you take this, for the Q exceptional genes, if you take the number, the value of the constant in constant times root n to the minus 1 log n to be larger, you need to, then you can get away with assuming fewer moments. Now, just to tie this back to a comment I made earlier, we haven't attempted at all to be economical in this analysis of the problem. I believe, as I said, because of the nice studentized ratio, that one can actually get these results under significantly fewer moment assumptions than we need. Although that requires better skill with the probability theory of self-normalized sums, and for the moment I can muster myself. So just to summarize, as long as these regularity conditions are satisfied, the conditions are essentially enough moments on the components, and as long as p increases no faster than polynomial as a function of n, then if I have exactly q components where the correlation is greater than or equal to a constant times n to the minus times the square root of n to the minus 1 log n to the minus 1 log n, and if all of the other components have correlation of smaller orders, have generalized correlation of smaller orders than that, then with probability converging to 1, as the sample size increases and the dimension of your vector increases, your ranking will always list will list the first Q components ahead of all of the others. And that's all I have to say. Thank you very much.
Thank you, Peter. We have plenty of time for questions.
Peter,
Hey.
Oh, sorry. Yeah, go ahead.
Oh, yeah, well, I'd be happy to hear what Peter's about to say.
No,
but
go ahead.
So you're looking at 6,000 and some odd correlation
Yep.
statistics.
Yeah.
And currently what people do is they look at things that are at least nominally T statistics.
Yeah. Yeah.
And they get an intuition of, how many false alarms they're likely to be seeing above a given level.
Yeah.
So you're replacing T by something that's kind of more like a square root of an F or something. I mean, it's out of it. You've got some number of degrees of freedom.
It's a T of a non-linearly computed thing.
Well, isn't there sort of a regression analysis with a fixed number of degrees of freedom hiding behind this? This is,
I guess that's true. I guess,
Doug and Art and I sort of think that back here.
It's not that. That's. I think I could be persuaded of that. Yeah.
So one thing that you didn't mention is, couldn't one just argue from it, level exceedances of things like F? You could tell people how many false alarms to be. I didn't see that ingredient in your methodology.
No, that's true. Yeah. I guess. I mean, what we want to do at some point, but I haven't thought of a real way of pinning this down, is to use the bootstrap calibration idea in order to give some neatly quantified account of false discovery rate. And that is something I want to do. I've thought about it a fair bit, but I've missed a way of doing that in a really convincing theoretical manner. But yeah, you're right, you haven't seen it, and it's something I would like to put in. At the moment, I haven't. I mean, I'm looking at that side of the methodology to try to quantify in some believable way the level, the impact of false discoveries.
Peter.
I guess I've got sort of two questions. One is when you're using cubic splines,
Yes.
you're essentially getting an estimate of the non-parametric conditional expectations you want. I mean, you're
Yep.
okay.
Yep. I think so.
Given
yeah.
given that you have done that,
Yeah.
why can't you go one step further and look at the Renyi correlation? Because that simply involves a further iteration.
That's a good point. Yeah. Actually, many years ago, I wrote a very small paper in the Australian Journal of Statistics about general measures of association, and that's how come I had contact with this literature. So I went back to that paper, which nobody else has ever looked at, and there's very good reason for that, I'm sure. And I looked at all the stuff. So that work was with Chandor Chorga, who you may know died a little earlier this year. He was a guy I liked a lot, and that paper cited some of this work, and there are somewhere between half a dozen and a dozen different approaches to generalized correlation. So the one that I've referred to here as generalized correlation is certainly not the one that I introduced, because the one I introduced was not as nice. This one was introduced previously in the 70s by somebody. But there's a lot of other approaches that one can use alternative to the generalized correlation that I looked at, and for each of which one can get a bit of mileage out of at least. And I would be very surprised if some of them weren't superior, at least in some respects, in terms of what they enable you to identify to the one based on the supremum of functions, which is, as I said, due to somebody else, not to me.
Okay. Maybe
You've got
just one further question, which is unrelated to this one. And that is one thing that I guess I think your method and all the other methods of this type misses the possibility of having two variables.
Yes.
Such that
Yes.
both variables
Yes.
are needed, and if one is present, then there's
Yes.
not.
I agree with you. You're absolutely right, and I have thought about that. But the thing that worries me, I don't have anything better other than looking at all possible pairs, for example, and then all possible triples. And you can see why this problem gets quickly out of control. I agree. You're absolutely right. And of course, on paper, it's a simple extension. And I bet I can give you moment conditions under which you can do that sort of thing. But its feasibility is challenging.
I guess in the other direction of the other questions, instead of making things more, I worry whether the fact using cubic splines actually is hurting you more than helping you. I mean, yes, it gives you the possibility of finding things which you might not find with linear correlation.
Yeah.
In your picture, like the top two genes had ranks of about the lower confidence rate with them was about 200.
Yeah.
So it is also the case that by using cubic splines for all genes, you fit more, and hence the precision of your information about all genes gets worse. So I wonder what that picture would look like if you have linear correlation.
Yeah, I think what you say is true, but I think it's if you want to go from a linear context to a nonlinear context, I think you have to spend something in order to get there. I mean, it's a little bit like in many statistical problems where there's a tuning parameter. The theory describes nicely what happens when you choose that tuning parameter outside the data, and some theory also tells you a bit about what happens when you choose it inside the data, but in practice, when you take that tuning parameter and you calculate it using just the data, that information doesn't seem to be usable again, at least not as readily as you would like in the next step of the problem. And that's what my answer to your question is that I think that there seems to be, you have to spend some of your information to make that transition from a linear to a nonlinear problem, and some of that information you use doesn't seem to be readily passable back.
Well, I agree you have to spend, but I'm wondering whether you spent more than you gained.
Okay. All right.
Well,
David, you want to?
Yeah, well, so what Rob is saying sort of plugs into what I was getting.
Yeah.
Okay, so, if everybody is traditionally trying to detect features based on T statistics where, it's basically the result of something like a univariate regression or
Yeah.
univariate
Yeah.
correlation.
Yeah.
And let's say we're going to try to extend that by turning each one of those univariate to where there's now a two-dimensional predictor
Yeah.
against a one-dimensional response. So
Yeah.
each one of those guys now has just one additional degree of freedom
Yes,
behind
yes,
it. Okay.
yeah.
So then what happens is, of course, you get the chance to find some feature you didn't have before.
Yes, yes.
But on the other hand, a rationally set threshold for all the other features has to go up.
Yeah.
And so what happens is, say you have one nonlinear feature and a couple or three things that would be perfectly well found. You could actually get yourself in a worse situation by adding in all those extra degrees of freedom. And I think that's probably what Rob was actually getting at.
Yeah. I agree with you, but I mean, what is the alternative? Is the alternative to restrict yourself to linear features?
Well, okay, so that's what we're getting at.
Yeah.
That the practical person has the choice of doing what people do now,
Yeah.
like T statistics
Yeah.
and univariate
Yeah.
correlation,
Yeah.
and you're kind of adding in multiple predictors.
I agree. Yeah.
Right, and they have to know which to do.
Yep.
And
Yep.
there's some trade-off,
Yeah.
so they need.
I agree. I agree that there's a trade-off. Yeah, and it's as I say, you add noise or you lose information or however you look at it or you lose precision, in some sense, by passing from fairly strict linear assumption to something more complex.
So if you're going to go to the picture of your p-value,
Sorry, of the
picture you had of
the graphs.
the graph,
Yeah.
so what might happen if you just restrict yourself to the linear correlations? No,
Yeah.
the bars. If you do the one where you had the bootstrap.
Ah, okay. Sorry.
So what might happen if you restrict yourself to linear correlations is that
There it is. Yeah.
you might not find the second guy, as you say, but the bars for all the group genes
Yeah.
are pushed up. So you'd have the intervals would be
Yeah,
shorter for
yeah.
everybody, but the ranking would be different.
Yeah.
The question
Yeah.
is-
No, I agree with you, and I guess in fact that's the point, isn't it? That if the rankings weren't different, you wouldn't have the potential of finding something new. Also, I guess I'm comparing the lengths of these prediction intervals only within one another for the case of cubic splines. I'm not comparing them with their versions for linear functions, for example. So, but if one was to make that comparison, it would be very tricky on the basis of what I've done so far.
Okay.
There's another kind of, when I've heard a lot of these talks, it brings up another kind of schizophrenia about these talks, which is you started with things like the lasso, which is a model for the joint effects of all of these guys, so that so the model says if x1 and x2 are highly correlated, it may be that only x1 is doing the predicting and
That's
x2
right.
isn't. If you knew how to fit such a model,
Yes.
that's why it's good to have a joint model.
Yes.
That's what it would tell you. However, it's a problem fitting such a joint model with high correlation. So you hear a lot of talks about, I'll just pretend any of the components that have, who in the joint model have a beta equals 0, aren't correlated. Their x's are essentially not correlated
Yeah.
with all the other x's.
Yeah. Yeah.
And then I can fit a joint model and discover things. Or we give up the joint model like you're doing here, and we do everything univariately, but then when you find two things that are highly correlated, you're left, they don't have, especially if you're ranking, you don't want to do ranking based on that, because there may be 5 important genes, but you may get 5 correlates of the top guy will win, and you'll throw away everybody else.
Yeah.
So you'll lose power to detect everything. So the question is, what is the right way, if we don't do these artificial things, to even pose this question? Because, you know, they're dealing with this question every day in genome-wide association studies. And except for the really hard problem that Peter brought up, how to start looking for interactions, nobody thinks they're doing too bad. I mean, in other words, they know the correlation structures of all these SNPs are very high if they're near each other. And they don't rank. I mean, they rank, but they use a cutoff, like David was saying, so which peculiarities are really significant. And then they sort of realize if guys are really close together, that's not additional information. They go look around what could be the causal gene around there. They just do it sort of real rationally. It doesn't seem an insurmountable problem. It doesn't seem like you need Elasto for that. I mean, I'm asking people. The problem's going to be when you want to look at two things at once. So I guess I'm asking the audience in general, what's the real problem here? And like, what are you doing about it? Those of you who are
Well, what's the
big data set.
yeah? What's the right way to model one response as a function of 5 to 10,000 variables when you only have a sample size of 30, for example? That's problem
Right,
is
well, they have much larger, yes, the genome-wide association has much larger sample size.
tens of thousands. Yeah.
Okay, I think Jamie has given us a topic for coffee. Beyond. So let's thank Peter again, and we'll
Okay.
return to the